Hi class, today's lesson is 2.5, graphing of rational functions. So what I wanted to do is to bring back yesterday's lesson about the restrictions. I mentioned something about these restrictions will lead to two things. And this is what we're going to explore today. If I get my highlighter out, ladies and gentlemen. Restricted values for rational functions will either be a whole, that's if things are canceled out, factors canceled out, or a vertical asymptote, which we will call VA. So just remember from yesterday that in order to find these restricted values, the denominator had to be equal to 0, which meant it was undefined. Then we took a look at the restrictions on a variable, because a constant number can't have a restriction, but on the variable. And then we also have to do today, we're going to add that on, that one of them is going to be a whole if it's canceled out, or it's going to be a vertical asymptote if it remains after being canceled. So let's take a look, folks. So it says here for wholes, wholes exist when a factor from a denominator is also in the numerator. So basically it cancels. So you might want to write that in. Whatever cancels, ladies and gentlemen, become a whole. So in this case, you start off with an expression, you have to factor it first, especially the numerator. So we factor the numerator, and we could cancel x minus 3 in both the numerator and denominator. So you let the canceled factor equal 0. So in this case, the x, your restriction would be x cannot equal 3. The reason it can't be 3 is because there would be a whole at 3. And in a couple minutes, we're going to do some of this on a graphing calculator to show you. Okay? And again, if we don't have graphing calculators at home, we can practice this in class with a graphing calculator. All right, so that's wholes. Vertical asymptotes, on the other hand, ladies and gentlemen, vertical asymptotes, okay, they occur when a factor from the denominator that has a variable in it still remains after it's simplified. So you may want to put down remains become a vertical asymptote, or VA. So looking at this expression, ladies and gentlemen, again, sometimes you can factor and it doesn't cancel. Okay, so in this case, there was no canceling, but what's left over is the bottom. So take a look at the denominator. Again, the denominator cannot be equal to 0, and since it remains, you let it equal to 0, and x cannot equal 1. So what does that mean, ladies and gentlemen? There's a vertical asymptote, or VA, at x equals negative 1. What we're going to do now, ladies and gentlemen, is please turn in your textbook to page 115, and we're going to use the graphing calculators to complete examples A to L. Okay? You may want to note that your homework here is page 112, numbers 2 to 5, and make sure you can identify when you have restrictions, which ones are wholes and which ones are asymptotes. Just a reminder, when you cancel a factor out, that's a whole, and when you have a factor that remains in the denominator, that's your asymptote. All right, ladies and gentlemen, so in your textbook, page 115, we're going to take a look at an example. First of all, remember to reset your calculators like we do in class. Okay? And in this case, we're going to set the window to some specific values just so we can get some nice graphs. Okay? So press window and enter these values in. The only one we don't have to worry about is the X resolution. All right? Great. Okay, taking a look at some of these questions, which is number 3. A talks about an expression, okay? X squared minus 4 over x minus 2. Look at the denominator, okay? It is a whole, okay? All right. Do you want to know why it's a whole? Because if you take this numerator, ladies and gentlemen, and you factor it out, you're going to have x plus 2 times x minus 2, which I apologize. I'm going to see if I can try and do this. I'm trying to do this at home, folks, so please bear with me. To try to equal it, And I try my very best. It's hard to do this with a mouse. Okay, I'm going to go x plus 2. Look at that, funny too. Okay, times x minus 2. Please work. I apologize, guys. This should normally be in here. It just didn't get included. Okay, and that's all divided by x minus 2. Oh, that's bad. Sorry, guys. Trying my best. Okay. What do we notice, folks, is that we can cancel a factor out. So we cancel the x minus 2 out with the x minus 2. And since it's canceled out, folks, that's why there is a whole. Okay? And the whole at x equals 2. Again, if you press a graph of that, ladies and gentlemen, you will find that it has that at x equals 2. Example B, ladies and gentlemen, we could plug in this expression, or we can simplify it out, and we notice that, again, this cancels out, so we have a whole at x equals 1. Please, if you haven't got a graphing calculator, if you don't have access to one, take this note, bring it in, and ask to borrow a graphing calculator so you can actually see where the holes are. It's pretty neat, and that shows you why there's a restriction. Okay, because you won't have a value at it. All right, moving on to C. Looking at C, 1 over x minus 3, there is a vertical asymptote at x equals 3. Because it's x minus 3, it's a factor in the denominator that remains. So what does that mean? It's a vertical asymptote, or VA. All right, looking at example D, 1 over x minus 2. Again, this factor exists. There's no way we can cancel it out. So we have a vertical asymptote at x equals 2. Moving on to E, I think it said to come up with an example where you have 2 vertical asymptotes. So again, it's 1 over x plus 1 and x minus 2. Again, you've got vertical asymptotes at x equals negative 1 and at x equals 2. Try graphing that one. That looks kind of funny. I think you get a smiley face when you do that one. F asks you to find an example where you have both a whole and a vertical asymptote. And again, you can make up any example here. I just chose one that we could easily factor and where there was a canceling. Okay, so taking a look, I just made an example up. Again, answers will vary here if you're trying your own. Okay, whatever cancels out, ladies and gentlemen, you set to equal 0, and it can't be because it's a restriction. So there's a whole at x equals negative 2, and the factor that remains, x plus 3, means that x cannot equal negative 3, is a vertical asymptote. All right, so again, try graphing that and see what you can come up with. It should show you the whole and the vertical asymptote. Just make sure you put brackets around each expression before your divide by sign. Great. Hope you're having fun with that graphing calculator because it helps you. G says to graph y equals 1 over x, and again you have what's called a horizontal asymptote, which is x equals 0. Now it asks you to move it up to, so again that's your C value, guys, that you move up. So it's 1 over x plus 2. So try graphing that, guys, and see how the horizontal asymptote moves up when you increase that by 2. Next example is H. How do you come up with an expression that doesn't have any holes or any vertical asymptotes? Well, basically you need to have no restrictions, therefore no holes or no vertical asymptotes. But you still want to have but we still have a horizontal one with this case, right? Okay, so what we need to do is to go linear. So try g at x equals x. Now we have no vertical asymptotes, no horizontal asymptotes, or no holes. So again, linear is easy. Okay, I and j, explain what we've learned today, that holes occur when restrictions are canceled and vertical asymptotes occur when restrictions remain after simplifying. Here's a key thing to know about K. When do you know when you have a horizontal asymptote? That occurs when you have a higher degree term on the bottom or on the denominator. So again, we know our reciprocal function, 1 over x. Again, degree 1 is on the bottom and a degree of 0 because there's no exponent on the top. Taking a look at this another example, f at x. I apologize, that should have a brackets around it. Put that in there. Okay. We have x squared divided by x to the third. Again, there's a higher degree on the bottom. What happens when we are looking for the second part? We have the same degree on the top and the bottom. Okay, so for a horizontal asymptote, you take a look at the numerical coefficients when they shift. So again, you've got 2 over 3. If you try graphing this, ladies and gentlemen, look for the horizontal asymptote, and it'll be at 2/3. Okay? Otherwise, if there's a higher degree, it's going to be y equals 0, and it's going to be on the bottom. But if they're of the same degree, then they're going to be that value, whatever the coefficients are. Here ends, ladies and gentlemen, our lesson for 2.5. Again, I'll restate the homework again. Page 112. Sorry, my page is not going down there. Keep going, keep going. Please stay with me. Thank you. For homework, page 112, numbers 2 to 5. Make sure you can identify when the restrictions are holes and when they are asymptotes. Again, it's important to take the time to plug this stuff in a graphing calculator so you can actually see, and it provides you a better understanding, ladies and gentlemen, of why we have to state restrictions. Also make note that if you're still struggling with your restrictions, please come and see me, because we are getting into more difficult stuff where we're going to multiply, divide these rational expressions. Okay? Here ends our lesson, and have a great night.